Imagine sailing through the dead of night, just stars above, and then suddenly the ocean around you starts to glow.
Not just a sparkle.
Right.
A steady, weird light.
Exactly. Stretching out, like, as far as you can see, these are Milky Seas, and they're this incredibly rare thing that sailors have talked about for, well, centuries.
Yeah, you hear these old accounts like Captain Kempthorne back in 1849 talking about a boundless plain of snow.
Or a sea of quicksilver. Even Jules Verne kind of hinted at it in 20,000 Leagues Under the Sea.
It's amazing, isn't it? What sounds like just, maritime folklore is actually real, though very elusive. We're talking huge areas of the ocean with this steady, uniform glow all night long. The scale is just immense sometimes.
But they're so hard to study, right? Because they happen so rarely and usually way out there, like the Northwest Indian Ocean or around Indonesia.
Precisely. That's been the big challenge. Their rarity, their remoteness.
And elusive is definitely the word. I mean, think about it. Fewer than 400 sightings recorded in 400 years.
That's not many at all.
And apparently only one known photo taken from sea level, and that was super recent, 2019.
That's right, for a private yacht. And the person who took it didn't even realize what it was until later, after reading about some research.
Oh, so you could see this totally bizarre thing and just not even know what you're looking at.
It really highlights the lack of direct observation we've had. Left so many questions unanswered for so long.
But that's changing now because of satellites.
Yes, exactly. This is where things get really exciting. We've got new satellite tech, specifically the day-night band instrument on satellites like Suomi NPP and NOAA-20.
Okay.
And these can actually detect the faint glow from space, hundreds of miles up. That's a game changer for studying them.
Absolutely. It takes Milky Seas out of the realm of, sea stories and puts them into something we can actually measure and investigate.
Empirically, yeah.
So that's what we're diving into today. We want to explore what science currently understands about Milky Seas, looking at these new satellite observations, and also this new database that pulls together all the historical sightings.
Right. 400 years worth of accounts. It's a fantastic resource.
Okay, so let's start there with those historical accounts. It's just wild to think about sailors encountering an ocean that looks like, well, like milk.
It really is. For centuries, these reports definitely had a sort of mythical feel. Imagine being out there, total darkness, and the sea just lights up like a snowfield.
Must have been terrifying, maybe, or just awe-inspiring.
Probably a bit of both. And this new database, put together by Justin Hudson and Stephen Miller at Colorado State, is so valuable. It gathers everything: old ship logs, the Marine Observer Journal, and now the satellite stuff, too.
Lets you see the patterns over time.
Exactly. Time and space.
And those descriptions. They're so vivid, like the sea turning to thick milk or cream.
Or glowing with green neon lights under the surface. There's one from 1854. Described the sea having turned to phosphorus and the heavens being hung in blackness.
Just incredible imagery. You can feel the atmosphere.
Definitely. And it wasn't just the light. Another thing that pops up in the accounts is this weird calmness.
Calmness? How so?
Yeah, many sailors mention the ocean being unusually calm during these events. One captain even said the water felt dense and solid, like molten lead.
Dense and solid? That's strange.
It is. And it might connect to something found during that rare research trip in 1985. They found the glowing bacteria, but also algae nearby that produced a kind of mucus.
Ah, okay. So the mucus could maybe dampen the waves, make the surface feel calm and dense.
That's a potential link, yeah. It could explain that molten lead feeling and the observed calmness.
So let's talk about the glow itself. The main suspects are bacteria, right? Bioluminescent bacteria.
That's the leading hypothesis, yes. Specifically, a species called Vibrio Harveyi.
And these are different from the kind of bioluminescence you see sometimes when you, disturb the water, those little flashes.
Exactly. Dinoflagellates cause those flashes when they're agitated. But Vibrio Harveyi are thought to produce a continuous, steady glow.
Which fits the descriptions of Milky Seas much better.
It aligns perfectly with both the historical accounts and what we see from the satellites, this sustained, large-scale luminescence.
And that 1985 research encounter where they actually got samples, that seems key. They found Vibrio Harveyi living on algae.
Yes, living on the surface of algae that were part of a bloom. This suggests they might not just be free-floating. They might need some kind of surface, an organic substrate, to really thrive and cause these events.
So maybe an algal bloom happens first, and then these bacteria colonize it.
That's a strong possibility. The algae provide the surface, maybe nutrients too, especially as the bloom potentially starts to decay. It sets the stage.
Okay, but how do tiny individual bacteria create a glow big enough to see from space? That seems like a huge leap.
Ah, that's where quorum sensing comes in. It's fascinating.
Right, quorum sense, like they're taking a vote.
Sort of. Think of
Yeah.
it like chemical communication. Each bacterium releases a tiny amount of a signaling molecule, an autoinducer. But the signal only really builds up when there's a whole lot of bacteria packed together a quorum, when the concentration of that signal molecule hits a critical threshold.
Which is what, like 100 million cells per milliliter? Something like that?
Around that number, yes.
Yeah.
Once it hits that point, it triggers a response in all the bacteria nearby to switch on their light production genes.
So they all light up together in sync.
Pretty much, it's this massive coordinated effort by billions and billions of bacteria all turning on their lights simultaneously. That's how you get that large-scale uniform glow.
Mind-boggling, just the scale of it. Okay, so we have the bacteria, we have the quorum sensing. How do we get from there to spotting it from orbit? That's the satellite breakthrough.
This is where the day-night band, the DNB, comes in. It's on the Suomi NPP and NOAA-20 satellites.
Yeah.
And it's just incredibly sensitive to low light levels.
Much more sensitive than older instruments.
Oh, absolutely. Orders of magnitude more sensitive. We're talking about detecting light thousands of times fainter than moonlight reflecting off the ocean. This sensitivity is precisely what lets us pick up that relatively faint, diffuse glow from the Milky Seas, even through the atmosphere.
But how do you know it is a Milky Sea and not just, say, city lights reflecting off clouds or atmospheric air glow or something else?
Good question. There are key signatures. Milky Seas tend to stick around for multiple nights, unlike clouds which move and change quickly.
Right.
They also drift with ocean currents, which we can model. And crucially, they're invisible during the day. Sunlight completely washes them out.
Okay, so you check daytime imagery of the same spot.
Exactly. If it's dark during the day but glowing at night and it persists and drifts plausibly, that's strong evidence. Plus, researchers use digital techniques to enhance the images, subtract background noise, really make the glow stand out.
Still sounds challenging, though. Does moonlight interfere?
Definitely. Bright moonlight can easily overwhelm the signal. That's a major limitation. The paddlights are also sensitive to air glow, which can sometimes look similar. Yeah, it's a faint emission of light by a planetary atmosphere. It can complicate things. And the satellite sensor doesn't perfectly match the exact color, the emission spectrum of the bacteria, so we might not be capturing the absolute full picture of the light.
Okay, so despite those challenges, they have spotted several events. Let's talk about some key ones. What about that 2013 one near Socotra?
Yes, that was a big one for confirming the satellite capability. August 2013, the DNB picked up this large glowing patch about 9,000 square kilometers east of Socotra Island.
9,000 square kilometers.
Yeah, pretty big. And the really compelling thing was watching it drift over 2 weeks, matching the ocean current models for that area.
And daytime checks showed nothing.
Just dark ocean. Confirmed it was nighttime bioluminescence.
Was there a link to algae there, too? I remember reading something about that.
There was. Not a direct overlap, interestingly. The highest chlorophyll levels, indicating the most algae, were often next to the Milky Sea, not right in the middle of it.
So maybe the Milky Sea forms where the bloom is starting to fade, or on the edges.
That's one idea. Perhaps the conditions adjacent to the peak bloom, maybe with decaying organic matter, are more suitable for the Vibrio bacteria to really take off.
Okay. Then fast forward to 2018, the Somali Sea event. That one looked different shape-wise.
It did. January 2018, both satellites saw this structure off Somalia. It started, then stretched into this long, thin filament along the coast, then curled into a kind of comma shape.
How big was that one?
Eventually about 15,000 square kilometers. And what was really neat was how similar it looked scale, shape, location to a Milky Sea reported visually by a ship, the SS Lima, way back in 1995.
Wow, like seeing history repeat itself through the satellite's eyes.
Exactly. And the 1995 Lima event was actually the very first time a Milky Sea was tentatively identified from space using much older, less capable satellite sensors. So seeing it again so clearly with the DNB was significant.
And the environment there. Any clues?
Well, the eastern edge lined up with an oceanic front, a boundary zone. It was sitting in cooler water coming from coastal upwelling.
Upwelling means more nutrients, right?
Typically, yes. And indeed, those cooler waters also had higher chlorophyll levels. So again, that link. Cooler, nutrient-rich, productive waters seem to be associated.
But the absolute giant seems to be the 2019 Java event. 100,000 square kilometers. That's like the size of Iceland.
It was truly immense, just staggering. And not just huge, but long-lasting, too. It persisted for at least 45 nights.
45
Yeah,
nights.
across 2 whole moon-free cycles, which helps with detection. And it was bright in some parts, almost as bright as moonlight from a crescent moon.
That's incredible. I read something about clouds appearing dark against it.
That's right. On infrared satellite images, which detect heat, clouds normally look bright. But here, the glow from the water was so intense that the overlying clouds looked like dark silhouettes against it.
Just shows how much light was being produced, and it was rotating.
Yes, seemed to be rotating slowly, clockwise, caught in this area of low water shears between big ocean eddies, like a giant glowing wheel.
And conditions. Similar story. Cooler water, algae nearby.
Pretty much. Associated with cooler water temperatures around 25 degrees C and moderate chlorophyll levels along the Java coast again, not necessarily right in the very highest bloom areas, but connected.
So looking at the map, these events seem clustered. Northwest Indian Ocean, Indonesian waters. Is there a pattern?
Definitely seems to be. The historical data, boosted by the satellite finds, really points to those 2 main zones. The Northwest Indian Ocean link seems tied to the monsoons.
How so?
The monsoons drive strong seasonal upwelling, bringing nutrient-rich deep water to the surface. That fuels massive algal blooms, potentially setting the stage for Milky Seas.
Okay, that makes sense for the Indian Ocean. What about Indonesia, the maritime continent? Is it also monsoon-driven there?
It's likely more complex there. The Indian Ocean Dipole, the IOD, seems to be a major player.
The IOD, that's like the Indian Ocean's version of El Nino, right? Temperature differences across the ocean.
Exactly. In 2019, the year of that huge Java event, saw a very strong positive IOD phase.
And a positive IOD does what in that region?
It tends to cause cooler surface waters and stronger upwelling in the eastern Indian Ocean near Indonesia. This can lead to really extensive algal blooms.
Ah, so the massive 2019 Java event happened during conditions known to cause big blooms in that exact area.
Precisely. And there was another Milky Sea detected simultaneously over in the Banda Sea, also in Indonesia, during that same 2019 IOD event. It suggests this large-scale climate pattern can be a major driver.
Okay, so we're getting a better handle on the where and when, but the how is still debated, isn't it? That older idea of just a thin surface slick of bacteria doesn't quite fit all the facts.
Right, the surface slick hypothesis has some problems, like how does it stay glowing if the wind picks up and makes waves?
Yeah, you'd think a thin slick would break up.
And sailors reported seeing light coming from below the surface when they scooped up water. Also, ships sailing through often didn't leave a dark wake, which you'd expect if they were disrupting a surface layer.
So if it's not just a slick, what's the alternative? I saw mention of a natural flask idea.
Yes, that's a more recent hypothesis trying to account for those observations. The idea is that the Milky Sea forms within a somewhat isolated chunk of water.
Isolated how?
By temperature and density layers like a thermocline below and maybe shear layers around it, these boundaries could limit mixing with the surrounding ocean.
Creating a contained environment, like a flask in the ocean.
Kind of, yeah. A stable zone where the water properties are fairly uniform temperature, nutrients. Within this flask, the bacteria could multiply steadily, reach that quorum sensing density, and glow without being easily disrupted by surface conditions.
And that could explain why it glows even in rougher seas, and why the light seems to come from deeper down.
Exactly. If the glowing bacteria are mixed throughout a layer, say several meters deep, surface waves wouldn't stop the glow, and a ship's passage wouldn't necessarily clear a dark pass through the whole layer. It fits the observations better in some ways.
That's a really interesting concept. Okay, so where does the research need to go now to figure this out for sure?
Well, the absolute gold standard would be getting shipped into these Milky Seas while they're happening. In situ sampling.
Right. Measure everything on the spot.
Everything. Temperature, salinity, oxygen, nutrients, organic matter, and critically, use instruments called bathyphotometers to measure the light intensity at different depths. That would really help test the natural flask versus surface slick ideas.
But getting a research ship to the right remote spot at the right time sounds tricky.
Extremely tricky. That's where other tech comes in. Autonomous underwater vehicles, AUVs, underwater drones, basically.
Uh-huh.
You could potentially deploy AUVs equipped with those light sensors in likely areas for longer periods. They could gather data continuously.
And the satellites guide where to send the ships or AUVs?
Absolutely. The satellites act as the scouts, telling us where and when to look. It has to be this combination of remote sensing and targeted in situ measurement.
Okay, last question, thinking bigger picture. Do Milky Seas matter? Ecologically, I mean. Do they tell us anything about ocean health?
That's still a big unknown, honestly. We don't really understand their ecological role or impact.
But the bacteria involved, Vibrio harvia, aren't they sometimes harmful?
They can be, yes. Vibrio harveyi is known to cause diseases in fish and crustaceans, particularly in aquaculture settings. It's considered a potential pathogen.
So, could more frequent or larger Milky Seas actually be a bad sign, maybe indicating conditions that favor this potentially harmful bacteria?
It's a possibility we have to consider. Are these spectacular glowing events maybe a beautiful but also slightly worrying symptom of changing ocean conditions? We don't know yet, but it makes understanding them even more important.
So wrapping this up, we've gone from these almost mythical sailor stories to using high-tech satellites to map these incredible glowing seas.
Yeah, it's a huge leap. From folklore to actual oceanographic phenomena we can study.
We've got a prime suspect for the glow Vibrio harvia bacteria working together through quorum sensing.
Right. And we're seeing connections to things like algal blooms, ocean currents, specific water conditions, and even large-scale climate patterns like the IOD.
But there's still debate about exactly how they form. Is it a surface slick or this deeper natural flask?
Exactly. The satellite detections are fantastic for showing us the where and when on a large scale, but we still need that ground truthing, that detailed sampling within the events themselves.
So many questions still remain about how they really work, what triggers them precisely, and what they mean for the wider ecosystem.
It really underscores how much we still have to learn about the ocean.
And it leaves you wondering, doesn't it? Are these just stunning natural wonders, or could they be sending us a message? A beautiful, glowing signal about the state of our oceans that we really need to decipher.
A very provocative thought to end on. There's definitely more digging to do.
Indeed. If you want to see some of those satellite images or read the research papers we talked about, check out our show notes for the links.
It's a fascinating area, and the combination of history, biology, and cutting-edge tech makes it really compelling.